welcome to the FME Fellowship Award Ceremony 2019. I have the honor, on behalf of the FME Board, to present to you the winner this year. Before I do so, I would like to say just a few words about the award itself. So, it is awarded approximately every 3 years. This year we are appointing a new fellow because we have this special event, the World Congress. So even though we had another one a year ago, or a year and a half ago, we have a special World Congress fellow this year. So the previous fellows are Cliff Jones, who is here somewhere, you must have seen him around. In 2018 we had Manfred Roy. So these are very distinguished colleagues who have been honored by their scientific breakthroughs, pioneering work, and by their contributions to our subject, to formal methods. They are nominated by colleagues in our community. These nominations are received and judged by the awards committee, and a recommendation is made to the board. So the fellowship is recognizing solid theoretical work, development of frameworks and tools, teaching formal methods, industrial applications, publicizing formal methods worldwide, and attracting people to the community. The fellows are people that have made distinguished contributions in one or more, in many cases, several of these areas. So, the award committee that I list here, and to which we are very grateful for their contribution, they collect these nominations and make a judgment based on those criteria. So I will now read to you a description of the fellow, and it will be a judgment on your literature review skills as to how long it takes before you can guess who it is. Let me see how you do. So, here's what I can tell you. The 2019 fellow is a leading researcher with seminal contributions in many fields of theoretical computer science and beyond, from general logics to vision algorithms for robots. His work is characterized by innovation, conceptual elements, and rigor, combined with practical applicability. Yeah? Okay. His scientific approach is best described by the dictum, "Beauty is our business." He is not afraid of venturing into domains far away from what we would think are his comfort zones. He actually relishes the opportunity to impose rigor on other fields and to encounter new challenges that inspire new theoretical developments. He is known for his seminal research on algebraic specification, concurrency, rewriting, logic, and computer security. The research of our new fellow is characterized by practical, simple, and intuitive computational logics and associated analysis methods and tools. The research results have been successfully applied to complex, state-of-the-art systems in diverse domains. His work on computer security is especially significant. His formalization of non-interference is one of the most well-known concepts in computer security, extensively used by both academics and practitioners. His paper on security policies and security models is one of the most cited papers in computer security, with nearly 2,500 Google Scholar citations. If you haven't cited it, yeah. He has worked on the design and implementation of several declarative languages, including OBJ and Mode, on formal specification and verification techniques, on concurrency theory, on formal approach to object-oriented specification, on parallel software and architectures for declarative languages, and on the logical foundation of computer science using equational logic, rewriting logic, and the theory of general logics. If you don't know now, you need to run to the library. He is the inventor of rewriting logic and the main developer of Mode. His fundamental contribution to formal methods has been the invention and development of rewriting as an expressive and intuitive computational logic and semantic framework for concurrent systems. In particular, the Mode 2 set is a practical high-performance rewriting tool. An important outcome is the demonstration that rewriting logic is a natural and simple model for concurrency. The simplicity and expressiveness of rewriting logic, as implemented in Mold, have resulted in the specification and analysis of a wide range of systems, including models of computation, different logics, and industrial programming and modeling languages. I'm sorry if I'm long. He worked a lot, so there we go. He has also made fundamental contributions to the formal analysis of distributed systems, combining state-based and action-based reasoning in temporal logic, combining rewriting with SMT solving, and providing theory-generic SMT solving algorithms that can be applied not only to fixed predefined theories, but to any theory that satisfies certain properties. More recent research contributions include cyber-physical systems, cloud computing, and biological systems. His friends and colleagues' testimony is that he tries to keep the highest ethical and scientific standards in his research and in his dealing with colleagues, his students, and other people around him. A nice man. New students are treated with the same courtesy as leading researchers. This is reflected in the fact that many former students continue to collaborate when they become more senior researchers. He is remarkably generous in sharing and discussing the many ideas emanating from his fertile mind, and is genuinely curious and appreciative of others' opinions. This collaborative spirit is also witnessed by him having 132 co-authors listed in the BLP. Despite being one of our generation's leading computer scientists, many of his collaborators, first and foremost, consider him to be a remarkably loyal and true friend. For all his academic achievements and his leadership and impact on the formal methods community, we present Professor José Messida, the 2019 FME Fellow. He is now going to say a few words. If I can change back to his slides, which I will do in a minute, I hope.
So, thank you very much, Anna, for such kind words. I am actually very moved, and this is not, I'm saying this from the bottom of my heart. And the other thing I want to say is that, as you have very nicely pointed out, a lot of my work is collaborative human work. So in receiving this honor from FME, I view it and understand it as really a recognition of that collective work, without which, I by myself only have done, very limited things. So I consider it in that spirit as something that I share with all these other persons. And since you asked me for preparing some kind of talk, I wanted to present to you some ideas about what I think is perhaps the best way of using formal methods. So, in some sense, even though I will be talking from the experience of my own experience, which is what I should be talking from, I hope that what I will present should be more broadly, perhaps useful in sharing with you the experience that I have gained. And I'm going to structure it by beginning with a few simple questions. Questions can be simple, but the answers may not be. Think about Fermat's theorem. It's a very simple question, takes time to answer it. So I will try to give my tentative answers to some of them, and then move to some concrete experience, in some way illustrating the ideas that I want to present. So here is question number one. What is the most effective use of formal methods? So we want to use formal methods, but we would like to maximize the efficiency of the use. And my tentative answer is the sooner in the design process, the better. So you will get much more payoff if you bring it very early into the design. One of the important reasons is that design errors are orders of magnitude more expensive and can be, failures in this can be much more disastrous than coding errors. So if you can detect these design errors at the design level, the impact, the beneficial impact of that can be much greater. And this has to do with the fact that sometimes we talk about system verification, and this is fine, but we may miss the point that verification is only part of the picture, and perhaps design is more important. And the reason for that is that the best use is not as what I would say a post-mortem autopsy of a bad design, but instead the main point is to reach good designs as early as possible by performing highly informative thought experiments. That's why I call my talk, the power of thought, of the thought experiment. Because when people design systems with their bare hands, they have very little analytic power or predictive power of how the system is going to behave. And then they may not be able to explore many designs because by the time they build it, they have already spent most of the resources and made many decisions that are very hard to change. Of course, this does not exclude, but rather empowers the use of formal methods throughout. So don't get me wrong, I'm not saying that we should only use it only on design. We should use it all the way to implementation and also, of course, to maintenance. But my main point is that it should start as early as possible, and that would be the greatest payoff. Okay, here's the second question. How can formal methods be used to perform this kind of thought experiments in system design? I'm using the word thought experiment. I think the person who, made that known broadly was Albert Einstein. So he called it Gedanken experiment in the theory of relativity. And the idea was that he could, in his own head, perform mental experiments that then would guide the actual experiments, that he would suggest to do, to confirm the theory of relativity. And the point of formal methods is that empowers designers and system builders to perform thought experiments about the system before it is built. So how can that be done? Well, I like to make a distinction that I think is relevant, and I think that it's worth distinguishing two levels of formal specification. One, system specification, which means where the specification is to specify a system, maybe a cloud computing transaction system, or a network protocol, or a microprocessor, different systems, different computational systems, or a biology, cell biology system at the molecular biology level. That's also something that a system like that could also be specified in that way. And then a second level is property specific. So the first one already gives you a mathematical model, that's the one you're talking about. Then once you have a mathematical model, then then you can talk about the properties. And you don't need to do both things in the same logical formalism. It may be beneficial to use what I would call a lean and mean simple logic, simple computational logic to specify the system, but then the properties, and you would like that to be executable. Instead, for properties, it doesn't have to be executable. It could be, higher order logic or temporal logic or many things like that. Because it's very wasteful to formally verify properties of either the wrong system or logically correct properties, but a system that is actually about design. That's perfectly possible. So you want to make sure that you have the right system before you invest maybe more effort, for example, in theory proving, about properties. So for that, executable formal specifications, so these are formal specifications in a logic, but have the advantage of being executable, can help a designer explore the system design space and look at different alternative designs quite easily by specifying and simulating different designs. And also, they can help obtain crucial information, so this is the idea of the thought experiment, about the system behavior before it is implemented by performing different kinds of formal analysis. And that's why that's what I mean by the idea of thought experiment. You can actually ask questions about the system before you build it, because you already have an executable model, mathematical model of the system. And these thought experiments may involve their correctness properties. Those are the ones that we most commonly think about in formal methods. But they can and should, for many systems, include also performance. Thought experiments about how well the performance of the system is going to be before the system is built. Okay, so here is the third question. What does this all have to do with rewriting logic, which is, also in the title of the talk? So the answer is that rewriting logic, as has already been displayed very nicely before, is a computational logic, which is very well suited for executable specification of concurrent distributed systems. And then mod is just a language that implements this logic, so that a program in mod is a theory implementing logic. And also comes with a formal environment, so that it can also, a system design expressed as an executable specification in mod, then can be formally analyzed in different ways. By simulation, so you can, is a model of your system that can be simulated and tested. Also by search-based model checking to see whether some invariants are violated by what's called the search command in mod. By explicit state or symbolic model checking in linear temporal logic and what we call the linear temporal logic of rewriting, which can also talk about actions or events, not only about the state-based properties. By statistical model checking, provided that the rewrite theory is extended with probability distributions about how the behavior of the rewrite rules execute. And so that allows to analyze performance properties of the system. And also by theory proving, using the standard first order logic for the equational part of the rewrite theory, Hoare logic, and a logic extending and generalizing Hoare logic called reachability logic. So properties can be expressed in these logics, and then theory proving, full theory proving can be carried out. Once the system is analyzed, system design. Once we have actually chosen among exploring the different, so I guess we can explore designs this way quickly, and then through this analysis hone in on a choice of a design that is optimal in some ways. Once we have done that, then it can be automatically transformed into a correct by-construction implementation. So here's the fourth question. What does this all mean in actual practice? That is, how has creative logic helped reach high-quality designs for real systems? So, well, I don't have all the time in the world. I was asked to keep the talk within some reasonable time bounds. So I cannot really give you a full answer, but I think I can give you some examples that of the usefulness of our experience in using creative logic for the design of systems that could give you at least a feeling and some general idea. And I will focus on two areas. One is browser security. So I will discuss the usefulness for both Internet Explorer and for the Illinois browser and operating system iOS. And then the other one is in cloud-based data store, which was also an area mentioned in the nomination. Well, I will explain how a completely new cloud-based data store can be designed, verified about its consistency properties, database consistency properties, analyzed about performance properties, and correctly implemented by automatic transformation. How, from the beginning to the end, the whole spectrum can be covered. Okay, so let's start with browser security, and then I will move on to cloud-based systems. So around 2007, hundreds of millions of dollars were annually lost by users of Internet Explorer by visual spoofing attacks, phishing attacks, things like that. And the team fixed the reported vulnerabilities as soon as possible. They were responsible and tried as soon as possible to fix those vulnerabilities. But because it's a system that has more than 1 million lines of code, they had no way to predict where the new kinds of attacks would come from, what else could happen. They were in some way in a reactive mode, just fixing, putting out the fires as they were happening. And they just had to wait for reports of mostly to then fix them as they were happening. So, Shuo Chen had taken my course on program verification. He was working in the area of security and then went to Microsoft's research. And through him, we talked and said, well, is there something that we could do, in applying mod to, some problem that would be relevant to Microsoft? And he said, yes, why don't we work together on Internet Explorer, the security of Internet Explorer? And then, I involved Ralph Sasse, then my student, now a senior researcher at ETH. And then he also involved some colleagues at Microsoft Research. And in a relatively short time, I am talking 2 weeks, we specified key functionality of Internet Explorer in mod. Now that's a little bit deceptive, because that was only possible, realize that Internet Explorer was private information of Microsoft, so we had no access to that. So there, the credit is for Shuo Chen, who spent, I think, 3 months reading code of Internet Explorer so that he could understand the functionality at the level of writing pseudocode. So that knowledge was essential and it was not available to us. But once we had that knowledge working with him, in less than 2 weeks, we had a formal specification in mod of all the basic functionality of Internet Explorer, which was executable and for which we could ask questions. And the main question we asked was what you might call visual invariant question. What is what you see, what you get? You may be seeing this others bar, but you may be in a malicious web page. And specify visual invariance of this what you see should be what you get kind of form, where the violation could be either a status bar spoofing or others bar spoofing. And out of that, we found 9 scenarios of status bar spoofing and 3 scenarios of others bar spoofing, so general forms of attacks, for each of which we could build a malicious web page demonstrating that this was for real. So they were fixed by Internet Explorer team, who asked us not to publish anything until all this was corrected. And we waited, and then we published in the Berkeley Security Conference a paper explaining all these problems, which is the paper that I'm citing below. And here is, for example, is one of the scenarios of others bar spoofing of a malicious web page that you could build in which a race condition would cause this kind of attack. So that analysis was a very useful, I would call post-mortem autopsy of Internet Explorer, but it was very useful because it really changed the situation, made these were all attacks that had never happened. Nobody knew about them. And so it made it secure about attacks that could have happened in the future, but we were actually ahead of time being able to predict that because of the power of the thought experiment. But of course, a status bar and others bar spoofing were just only a particular kind of security attack. There were other possible vulnerabilities, but given the size and complexity of Internet Explorer, fully verifying Internet Explorer was not feasible, not something that could be reasonably done. So then what happened is that positive experience encouraged one of my colleagues in my department at the University of Illinois, Sam Hill, came and talked to me and said, well, so he worked in browser and operating systems, so he was a systems person, and said, well, why don't we do it right? I mean, why don't we work together on designing a secure browser from the beginning, using formal methods, using mod, and let's do it. And so that was he involved one of his students, Shuo Tang, who also took my program verification course, so he was both knowledgeable about browsers and knowledgeable about mod and formal methods. And I involved my student, Ralph Sasse, who was, had a stronger background in formal methods, of course. And then we asked the question, could formal methods help from the very beginning in designing and implementing a secure by design browser? And the answer was the IBOS system. And we answered that by expressing and analyzing the different alternative designs in mod, and then going through different design alternatives, using mod as a way of exploring those designs, and then designing a small browser that had a small kernel. So the implementation had only 60,000 lines of C++ code in the kernel, and to enforce all the security. And then specifying 11 security properties, culminating in the same auditing policy, and verifying them. And then implementing and demonstrating the browser. So there was a browser that was actually built and demonstrated in performance and functionality as an academic project. So it's not a browser that has become a commercial browser, but it was a fully implemented and demonstrated browser. And this is kind of the architecture of the browser. You can see the kernel below, and then the network processes, and the kernel essentially control and check every interaction between the different, the user interface, the input-output, the network communication, and the different processes that were established. Now, the security properties, these 11 security properties, were formally verified with respect to the mod design and specification in two different ways. The first verification was done by Ralph Salce as part of his PhD thesis, using model checking in mod, using an abstraction. So he built an abstraction of the system and then proved the correctness of the abstraction, in a mathematical theorem, and then verify all the properties. More recently, in work soon to be, just in a matter of weeks, filed as a PhD thesis, my student Stephen Skerrick has completely finished a full theory-proving verification in reachability logic of the same properties. So we have first a model checking verification, and then more recently a theory-proving full verification of the security of the browser. So now I'm going to move to the second area where I want to also give you some experience, which is the area of cloud-based data stores, which of course, is happening, in the internet, everywhere. It's a huge kind of thing, but it has a number of important requirements, right? So data must be always available because of network failures and network congestion and schedule upgrades and so on. Data must be replicated, and is a huge area. So Facebook in 2014 had 300 petabytes of data, and then the number of photos updated was also huge every day. And data, of course, must also be partitioned. So it's stored in different data centers. And then, of course, one of the key problems is the problem of consistency, because the replicas of the data should be consistent with each other, should have the same value. But there is a well-known, in distributed systems, a well-known theorem called the CAP theorem, saying that you cannot have consistency and availability and partition, tolerance together. Those three things are impossible together, so something has to give up. You have to give up or relax that. And in practical terms, what it means is that these data storage systems, to have enough quick response, to a client using, buying something on Amazon or Facebook or whatever, there has to be a trade-off between consistency and latency. You cannot, ask for, the traditional ACID full consistency requirements of a distributed database, because that is not going to work, in the internet, with millions and millions of people, interacting. So the whole game here is that depending on the kind of applications we're talking about, because it's very different to, say, talk about financial applications in a bank or medical applications in hospitals than, say, Facebook. Depending on the kind of applications, you will have a certain level of consistency that may not be full consistency, but maybe the level that is reasonable for the application. And what you will trade off with that is that with weaker consistency, you can have much better, shorter latencies, and therefore availability and response of the system, which may be crucial, because if you have, some commercial system on the internet and, it doesn't come back to you in a minute, many people will just have left that and go somewhere else. So it's very important to understand that in this kind of systems, correctness relative to some consistency and performance go together. Because you could have a perfectly correct system that is totally useless. So the design has to address, and formal methods have to address simultaneously the two things. to really be satisfactory and useful. So we have been working in a collaboration of researchers. You know, my colleague Indi Gupta is one of the professors in distributed systems, his students, my students, and then Peter Olveski at the University of Oslo, and also his students. We have been working together as a team in using mod to analyze and design, in some cases, cloud-based storage systems. And in my experience, this is to be actually one of the earliest applications for mod methods in this area, because we have been at this for maybe 8 or 9 years now. And it has been actually quite a positive experience. And to deal with this trade-off between consistency and latency, which has to be balanced, on the one hand, we have to address the correctness of the desired degree of consistency. So the design will say, well, we settle for something, one of the weakest things, which is eventual consistency. But at the end of everything, with all transactions are finished, then they will be consistent. The different replicas will have the same value. At the top, we'll have a strong consistency, but there is a whole, range of intermediate possibilities. And depending on the application, the balance between the two things will be in a different point at that level. So therefore, the analysis has to address both things: the correctness of the consistency properties and the desired performance. And the way we do that is we first use formal executable specifications in mod to specify alternative designs of the system of a given distributed data store, and to simulate it. Then we model check the desired consistency properties using mod and the model checking capabilities of mod. And then the alternative designs can be compared for performance by statistical model checking, where we enhance or enrich the rewrite theory with probability distributions for example, how long will a message take to arrive from one place to another, things like that. And then, when possible, we also compare the performance estimates obtained by statistical model checking with the actual performance measurements of actual implementations to validate the predictions at the performance level as well. So that's kind of the flow of the way we use mod this way. So, for example, in this way we have specified and analyzed a key distribution service on top of Zookeeper. We analyzed, we believe for the first time, the Cassandra system and also an alternative design. And that was a lot of work because Cassandra has more than 250,000 lines of code and no formal specification of any kind and no documentation in detail. So the students of Gupta and my students spent about a year reading the code so that we could, from that, obtain what, collectively studying the thing, we consider was a faithful formal specification of Cassandra. The Google Megastore and also an alternative extension. This was work done at Oslo by Peter Olveski and his PhD student. So where we designed a fairly extensive new extension of Google Megastore. The RAM system of Berkeley and a number of design alternatives to it. PSTOR, where actually an error in the algorithm was uncovered. The Walter system, which was analyzed and compared to Rolla. So Rolla is a completely designed, done by my former PhD student, C. Liu, who is now a postdoc at ETH. Some of the papers. There's a survey paper, which is the first one there, which gives a survey of most of this work. And then on Rolla there is a Fasse paper, and then also his his PhD that I will mention in the next slide. So those are the systems that we have thoroughly analyzed in all these different ways. And in the case of Rolla, design, analyze, and build. That's what I will tell you in a moment. So I think I would want to focus on Rolla because it's the most interesting in the sense of covering the whole spectrum from design to implementation within mod. And also because it's completely new, nobody had done it. So we designed it, formally analyzed it, compared it with Walter especially, which was the alternative, and also implemented it entirely within mod. So Rolla came about in the following way. As I mentioned, between eventual consistency and strong consistency, there's a whole bunch of different possibilities. And in particular, there are two properties called read atomicity and causal consistency, which, then, both imply, parallel snapshot isolation and these other two properties are guaranteed by a system called Walter, which is one of the ones we had analyzed. But something in the design space that had never been done, had been conjectured in the paper by Cerone and others, was that, well, maybe there could be an algorithm that could provide the first two properties, read atomicity and causal consistency, without having to guarantee PSI. Would that be possible? What would the system would be like? So that was conjecture. And so Rolla is the answer to that conjecture. And for certain applications, let's say Facebook or whatever, is a very reasonable choice. And then the question is, well, yes, but Walter gives you this extra guarantee. So could we, in this trade-off, have a slightly weaker consistency but more performance? Okay, compared with Walter, which was the one providing all the three possibilities, and then C. Liu, a PhD student working with me, who finished his doctorate in May, answered this. He designed and simulated Rolla in mod. So this is a new design that he came up with. Mod, in some way, this is the last work he did, but he was involved in all the other systems, so he already had gained enormous knowledge about the different design alternatives within this whole space. So he was in a very good position to do that. Then model check the RA and causal consistency properties of the design, and then analyze performance through statistical model checking, showing that outperforms the Walter system. And then, on top of that, he developed, also in work with Peter Oleski and with my help, a general correct by construction theory transformation, so that you take a theory in mod and you transform it in another theory that, because mod supports also distributed execution on several machines through TCP/IP sockets, then gives you a distributed implementation of the system, which is bisimilar to the original specification and therefore satisfies exactly the same properties. And then he showed that that implementation was consistent with the performance estimates that he had obtained by statistical model checking once experiments with the implementation could be carried out. And so this is documented in his PhD thesis at the University of Illinois. And just to give you a feeling, I'm going to show you a couple of slides. One is how Rolla outperforms Walter. So these are all the different statistical model checking comparisons, and in all of them, the new design is consistently more efficient, has better performance, than Walter. And then the other question, always, which we have done not only for Rolla but for other systems, is okay, how good are these performance estimates relative to an actual implementation. And well, I can tell you what you can hope to obtain and what you cannot hope to obtain. You cannot hope to obtain the exact same curve because the parameters that you're choosing in the statistical model checking are not necessarily, for latency, for how many processes and so on, are not necessarily the same as the one that you would do in the experimentation. What you should be able to expect is complete similarity of the curves. So they need not be identical, but they could be very similar to each other. So here is the way the comparison looks like. So the upper part is the statistical model checking, and the lower part is the actual implementation, distributed implementation in mod. So here, the code running is mod code. And as you can see, they are not identical, but they are very similar, a complete similarity between them. And that's the best you could hope for. Okay, so I think I have now given you some examples of our experience in this idea of the thought experiment, how to use executable specifications early in the design process to obtain a high quality design as early as possible, as quickly as possible, and with much less effort than in the traditional way. And here are some, I would say, takeaway thoughts that I would suggest, to summarize all this. The first one is that formal methods can empower system designers with the power of thought experiments. That such experiments can be performed on system specifications which can and should be executable. So being executable really is very important for this. Then also that these formal executable specifications can be analyzed for both correctness properties and performance properties, and for certain systems like say cloud computing systems, this is crucial. And then also implementations that are correct by construction can be automatically generated from executable specifications. So that what you might call the formality gap between the level of formal specifications and the level of the actual implementation is completely bridged. There is no gap. And then what I would say is that the more experience shows that all this is possible for real systems, as I have tried to illustrate with these examples. But I don't think the main point is mod or rewriting logic. The main point is that this experience could be of use to people using a different formal approach, other alternative approaches, because don't depend on the particular choice. Of course, the choices that we make of tools make sense, and we have good reasons to make those choices, but they are not the only one possible, and this could be similar possibilities could be used in other approaches. And I just want to say thank you very much for this opportunity, this honor, which I'm deeply grateful for.